Hello, this is Professor Gavoor. Today we're going to cover Little's Law and some inventory models, including economic order quantity. The agendas will be as follows. Little's Law. We'll have a little overview and review of what we've already covered on inventory. And then talk about two simple inventory models, economic order quantity and single period inventory. John Little, who was the creator of Little's Law, was born in Boston in 1928. He got his undergraduate degree in physics from MIT. He worked at GE and then got a PhD and was the first person to get a PhD in operations research. And his dissertation was the use of storage water and hydroelectric systems. He taught at Case Western University from 57 to 62. And he joined the faculty at MIT, where he's been, I think, a professor since. He was a visiting professor in Europe at INSEAD in 1988. His formula is very simple. It involves three variables: flow time or cycle time. And that's the average time it takes to complete one cycle of a process, or to process one unit or one item or one person. Throughput, as we discussed last week, was the number of items or transactions processed in a unit of time. So it's actually a rate. Work in process is the number of items or transactions being produced or transacted. Basically, it's how many items or units or people are lined up awaiting, either being processed or waiting to be processed. Flow time or cycle time, as we said, is the average time it takes one complete cycle of a process. The simple formula explains the following: the relationship between flow time, throughput, and work in process. So the number of people waiting in line, or items waiting in line, or items in a system, work in process, equals throughput times flow time. So we have a rate times a processing time, and that will tell you approximately how many are in the process at any given time. And this is on an average. This is taking, kind of a long range view of things. There are only three possibilities for this problem. You are given two or three of the variables and have to figure out the third using the base formula. So if you're given R and T, we must calculate work in progress. So if you're given throughput and flow time, we have to calculate work in process. The basic formula is what you use here. Work in process equals R times T. So if you know R and T, you can figure out what WIP is. If you're given WIP and R, you must figure out what T is. So solve for T in the base equation, you get T equals WIP divided by R. And if you're given WIP and T, you have to determine what R is. And it's R is equal to WIP divided by T. So now you're all ready to go. How to determine the variables in a story problem, which is what all these problems kind of sort of are. Well, work in process is always the number of units, items, or people waiting in line and being processed or served. It's how many are in the queue, how many are in the actual process of either waiting or being served on. Throughput stands for rate. They use the word R. R stands for rate. So it's the rate at which a unit, item, or person is processed. It's items per unit of time. So it's always a rate. As soon as you see the word per hour, per day, per mile, hour, per second, per minute, per week, per day, you know that that's the rate. Flow time is the amount of time it takes to complete one cycle of the process. The time to produce, serve, or process. There we go, spelling correction on the fly. Once it is being processed. This is a measure of time too. It's not a rate. So you should have, if you're looking for WIP, they're going to give you a rate and something that's not a rate. And if we, some watchouts in story problems or professorial curveballs. R and T have time in them, but one could be in minutes, the other in hours. One could be in seconds, the other in minutes or hours. Hours, one could be in hours, the other could be in days. One could be in weeks, the other could be in months or years. Conversion will need to be done to have R and T in the same units of time. Also, the rate could be in one unit of measure of an item, and T could be in another, so they must be the same. And we'll look at some examples now. A voting facility processes an average of 50 people per hour. It takes 10 minutes on average to complete the voting process. What is the average number of people, of voters in the process, waiting in line and or voting? A facility processes an average of 50 people per hour, and it takes 10 minutes on average to complete the voting process. I'll give you time to work on this problem. You should probably pause the video and work on it. Well, if we look at it, the solution is 10 minutes equals T. It's not a rate. It takes 10 minutes to complete the voting process. That's how long it takes to process one voter. And it's an average. And that's what we're using as the average. Some people take 8, some people take 12, but the average is 10. 50 people per hour takes an average of 50 people. A voting facility processes an average of 50 people per hour. People per hour, well, that's a rate. That's the throughput. They process 50 people per hour. Oops, let's look at this. T is in minutes, R is in hours. Have to make them the same. So 10 minutes equals 1/6 of an hour equals T. Now you have 1/6 of an hour and 50 people per hour. We can do this. We know R and T, therefore we have to calculate WIP. WIP equals R and T, so we have 50 people per hour times 1/6 of an hour equals 50 divided by 6 people. The hours cancel each other. I have an hour in the numerator and denominator, they cancel. So I have 8.33 people in line and voting on the average. There's 8 people either voting or in line waiting to vote at any given time. And again, this is on average. Let's have another problem. A loan department takes an average of 6 days to process an application. And we know that, on average, there are 100 applications in the pipeline. What is the throughput of this department? Well, I know we're looking for throughput. So throughput equals WIP divided by, throughput is R, so R equals WIP divided by T. So we must know what WIP and T are in this problem. Again, pause it, solve it, and come and look at the answer. That was giving you time to pause it. Here is the answer. You have to determine throughput or R, and it equals WIP divided by T. 6 days is not a rate, so it therefore must be T. 100 applications are in the pipeline. That must be WIP. That's the queue. That's the queue and those applications being worked on. So R equals 100 applications divided by 6 days, or 100 divided by 6 applications per day. Or if you do the math, 16.7 applications per day is the throughput of this department on the average. Next, a restaurant makes 400 pizzas a week. Each pizza uses a half a pound of dough, and the restaurant typically keeps an inventory of 70 pounds of dough. What is the average flow time or processing time? Well, here we go. We're looking for the average flow time, that's T, so we must know what WIP and R are, and T equals WIP divided by R. We have 400 pizzas per week. That's good. And each pizza uses 5 pounds of dough, and a restaurant typically uses 70 pounds of dough. So 70 pounds must be the queue of pizzas being ready to be made into pizzas. let's pause and you try it and come back after the pause and see what the answer is. That was time for you to pause it. Now let's advance the slide. Well, we're trying to find T, which equals WIP divided by R. R equals 400 pizzas per week. It's the only rate in the problem, so it has to be R. WIP equals 70 pounds of dough. But we have pizzas is a unit of measure in the rate, but dough is the unit, pound of dough is the unit of rate, or is the unit in the WIP. They're not the same. So I have to change the 70 pounds divided by 5 pounds per pizza. So I have 140 pounds of, or 140 pizzas equivalent of dough in the process. So my processing time, my through time is 140 pizzas divided by 400 pizzas per week. So it's 140 divided by 400 weeks, or I get 0.35 weeks. 0.35 weeks makes no sense to me. So let's turn that into days. There's 7 days per week times the number of weeks. I would get 2.45 days coverage of pizza dough. 2.45 days coverage of pizza dough. Now, it's supposed to be processing time. You got to be a little careful here, because sometimes it's processing time, sometimes it's the amount to process the amount of the WIP, in this case, pizza dough. So it's coverage. That pizza dough covers you for 2.45 days. Okay? Now let's look at inventory. First, we're going to start with an overview and review of what we've talked about before. Inventory management decision. Well, the right time to order items from a supplier, or the right time to produce goods yourself, and the quantity required to order each time a supplier order is placed, or the quantity of items required to produce each time you have a production order in place. So in order to have the right products in the right time at the right place at the right quantities, you have to be able to make these right decisions about how much to order if you're buying from a supplier, or how much to make if you're making it yourself. What should your order size be? What should your manufacturing batch size be? So categories of inventory costs. There's ordering costs if you're buying it from someone else, or setup costs. The factory is idle while you're changing over to produce the item that you want to make. And ordering costs, while it sounds trivial, because what does it take to order something on Amazon? It takes no time at all. You just go on Amazon, you buy what you want, so it seems like there's no cost at all. But when you try to buy airplane tickets, if you can remember to a pre-COVID era where that was possible, well, then you could tell that it sometimes takes you a long time to buy airplane tickets. Shopping around for the price and this, that, the other thing, looking at American versus United, looking at this website versus that website, and it could take you a fair amount of time to find the right value, right number of stops, right price. So it's a non-trivial time ordering costs. And inventory holding costs, or inventory carrying costs. The longer you keep product in your warehouse, it has to pay rent to pay for that warehouse. It's absorbing the fixed costs of that warehouse operation. Then you have shortage costs or stockout costs. What if you go out of stock? Well, you've lost sales. And then what is the unit cost of the item that you actually are buying or actually are making? So these are the kind of costs that kind of contribute to inventory. So number of items, the characteristics we look at is the number of items, nature of the demand, number of and duration of time periods, lead times, stockouts, all of this kind of stuff is what we look at. Number of items. Each item is identified by a unique identifier called a stock keeping unit, SKU. We have talked about this before. It's the barcode thing, single item or asset stored at a particular location, or many locations depending on how much inventory of that item you have. Nature of the demand. Is it independent demand? Is it dependent demand? Is it static demand or dynamic? Independent is the demand for an SKU that is unrelated to the demand for other SKUs, and it needs to be forecast. Dependent demand, so think of bicycles as I'm a bicycle manufacturer. Bicycles are my independent demand. I have to forecast how much I think I'm going to sell. But once I know how much I want to sell, then I have dependent demand. If I'm going to sell 500 bicycles in the next month, well, and let's assume they're all the same. There's only one SKU I'm looking at of bicycles. For each bike, I need a set of handlebars. That's a dependent demand. So I need 500 handlebars. I need 500 times 2 number of wheels. These bicycles have 2 wheels. That number of inner tubes, that number of tires, etc. You see how it goes. I need 1 saddle post. I need 1 saddle per bicycle. Those are all the parts of the bicycle are all dependent on the number of bicycles I forecast that I have to make. Static demand is demand that is stable in nature. Prescription drugs are static. You're going to take 1 or 2 or 3 pills of a prescription per day, and if it's a kind of a lifestyle prescription like high blood pressure, hypertension medicine, you have to take 1 a day. It's a static demand. You get 90 days supply, and when that 90 days is almost out, you order some more. But you order another 90 day supply, which is just 90 pills. Now, of course, you might forget to take it. If you're too old, you might take 2. But mostly the demand is static. Dynamic demand is demand that varies over time. And right now, we're going to talk mostly concerned about independent demand, the kind of demand we have to forecast. Number of duration of time periods. Well, firms, as we talked about, plan their inventory over extended time periods. The most common time period over which we plan inventory, and I'm going to refer to autos, at the larger kind of a macro level in a company, is a month. Now, when you get into the factory, you're planning more by weeks and days, because that's how your production planning goes. But for inventory planning, a month seems to be the most used time period. Then we look at single period and multiple time periods. Right now we're going to do multiple time periods. We're just month after month after month. We're going to look at single period inventory as a separate model. So the lead time is the time between placement of an order and its receipt. So if I place an order from a supplier, I send, like when you place an order to Amazon. Well, you're going to get it the next day or 2 days later or however you specify the shipment. That's the lead time. So if I want to buy something at Amazon and I know that it takes me 2 days to get it the way I usually buy it, I better order it 2 days before I think I need it. That's the lead time. You have to take that into consideration. So it's transportation carriers, buyer order frequency and size, supplier production schedules. Also, when I decide to produce a good, it takes me some time to get that good into production. I can't, some things you can make instantaneously or almost instantaneously, but others takes a fair amount of planning. So when the decision is I need to make some more of this product, what's the lead time? What's the average lead time between that and the start of production? So I've got to take that into account. Stockouts, inability to satisfy the demand for an item. A back order occurs when a customer is willing to wait for an item. Lost sales occurs when a customer is unwilling to wait and purchases the item elsewhere or reorders it more likely the next time they order from you if it's business to business. In consumer goods, there used to be a lot of back orders, but most consumer good companies have eliminated back orders just because they're a pain to have to deal with and model for. ABC inventory analysis is really kind of an important thing. We categorize inventory into two groups according to the total annual dollar volume of sales. A items, and you want to rank order all your items from the one that sells the most to the one that sells the least. So it's a decreasing ordering of items. Your A items account for a large dollar value, but a relatively small percentage of the items. Example, 10 to 30% of the items account for 60 to 80% of the total dollar value. It's kind of a Pareto's law here. And who was Pareto? Pareto was the Italian economist who said 80% of the wealth is in the hands of 20% of the people. The other 80% of the people only have 20% of the wealth. And it's like that, don't you think, in economics? A small number of people are really rich, and the rest of the people share in whatever they don't have. So you look at A items. A items are your big sellers. They're probably the number of items that account for the top 80% of your sales. That's usually the rule of thumb most of us use. C items account for the small dollar value, but a large percentage of total items. And this is so true in consumer goods, almost across the board. They're probably 50, 60, 70% of the items, yet only make up 5 to 15% of the dollar value. So companies I've been with, A items are the top, if you rank order your sales from highest to lowest of items that you sell. The top 80% are your A items. The bottom 5% are your C items. And the middle 15 that aren't A and aren't C are your B items. And they tend to be 15% of sales. So you have a large number of SKUs in C, a smaller number of B items, and a much smaller number of A items. You ask the question, why don't we just make A items? Why are we bothering ourselves with the C items? That's an ongoing concern, question, struggle between sales and marketing all the time. Now, if I'm making Cheerios or jams and jellies or those kinds of things, dishwashing liquids, it's a really good thing to talk about. Do I really need all those other things? Like we talked about Coca-Cola and Pepsi really getting rid of their zombie brands because of the constraint on aluminum can production and filling due to the COVID. You know, most people are not buying as much soda outside at fountains as they used to. So they're buying more cans, and there's not capacity, or there was not capacity early on to account for that massive shift. So rather than sell B and C items, everybody in the company got their act together and got rid of all the funny flavors of Cokes and Diet Cokes and Zeros, and focused basically on producing the regular Coke, Diet Coke, and Coke Zero only in the various can counts and manifestations thereof, but it just made it more simple. And you can do that for something like that. But if you're making shoes, well, you have to carry every size, every width that you are planning to sell to the population that you're planning to sell to. So you can't just say, well, I'm going to get rid of and some of those are going to be CSKUs. A size 6 triple E men's shoe may not be a really popular seller, but you have to make it for the few size 6 triple E customers that are out there if you want to sell them shoes. Most of your ASKUs are going to be shoe sizes and widths that a vast majority of the people wear and are more popular, but you have to cover those for everybody. So it really depends on the size and nature of the business, how you trim your offerings. The other thing that we don't include is slow and obsolete. SL for slow, OB for obsolete, slob. Those items aren't usually classified A, B, or C. Mostly the slow items will be C items. but that inventory becomes its own classification you want to look at. And you probably look at them separately, slow and obsolete. Some people call them E and O for, I forgot what the E means now. How could I possibly do that? Excess and obsolete. I like slow and obsolete because slob is the kind of inventory you're talking about. That extra inventory because of poor planning, you're now overweight with inventory. All right, so let's talk about economic order quantity. There was a guy named Ford Harris in 1913 that wrote a paper about inventory, economic order quantity of inventory, or economic production quantity of inventory. Every inventory model that's based on mathematics has a root in Ford Harris's original inventory paper from 1913. And the economic order quantity model, which almost no one uses, but everybody learns in school. The reason almost no one uses it is it's pretty simplistic. It's like the crazy uncle problem, back of the envelope, almost kind of calculation. Most real life models have further needs. They need, and I'll explain to it when we look at the assumptions. So it's a classic economic model that minimizes the total cost, which is the sum of the inventory holding cost and ordering cost only. Like I said, it was developed in 1913 in Factory Magazine, in an article by Ford Harris. And why only inventory holding costs and carrying costs? Well, we assume in this model that the price is fixed for an entire year. So price times the quantity that you're going to use, and you also know what the demand is for that year, which is really nice to know what the demand is going to be for the next year for something. So you know the demand, and you know the price at which you've negotiated for the following year. So demand times the price is kind of a fixed cost. That cost is not going to change. The only thing you can change is how often do I order and in what quantities. So there's a cost of ordering. So the more I order, that cost goes up. And there's a cost of, if I have too much inventory, I have to pay rent in the warehouse for that, which is the carrying cost. So that's the only costs that are involved here. Key assumptions, only one SKU is considered, and the entire order quantity arrives at the inventory at one time. And replenishment is instantaneous, so you don't have to worry about lead time. Those are another key assumption. Probably should put that in there. Lead time is 0. There is no lead time. So, given those assumptions, just like the crazy uncle problem, we had assumptions, you can get a good feel for how many times you're going to order, what size your order should be. Order setup and inventory are the only costs. No stockouts are allowed, so you don't have any back orders. Demand for an item is deterministic and continuous over time, so we know what our demand is for the year. We forecast it, we know. Who has that luxury? Most people don't. And lead time is constant, and which is 0 in this case, in the base case. So cycle inventory is a result of from purchasing or producing in large lots, in larger lots than are needed for immediate consumption or sales. The average cycle inventory is the maximum inventory plus the minus inventory divided by 2. And if we take the inventory right down to 0 and then replenish it instantaneously up to the maximum, the average inventory in the system is going to be quantity, that maximum quantity, Q, divided by 2. And the model looks very much like this. We have a certain amount of maximum inventory. We draw down from that inventory in a linear way, so nicely, so beautifully. When we hit 0, we instantaneously replenish up to the maximum inventory and draw down in a very metered, even manner, so you get whatever that slope is of usage. and then we order again. So we have this sawtooth kind of thing. Our average inventory is Q2. This is time across here. This is your minimum inventory level, which is 0, which is also not real. Sometimes if you're going to want to order around here so that when you get to 0, your order arrives. That's called a reorder point. Right now our reorder point is 0. You get to 0 and voila, everything instantaneously shows up. So you can see how this base model doesn't have the greatest application, but you keep adding things to the equations and you end up with something that works very well. So inventory holding costs. Cost of storing 1 unit in inventory for the year is CH, C sub H, and it equals I times C is another way to look. Sometimes they give you CH, sometimes you have to figure it out. I is the annual inventory holding charge expressed as a percent of unit cost. This is what a lot of accounting people will do. They will say, okay, what's my annual, let's take a percentage of annual cost of this item and assign that as the holding cost. So maybe it's going to be 5%, 2%, 1%. It's small numbers depending on what the item is and how much space it takes up in your warehouse. The holding cost for a Bic or Papermate throwaway pen is not going to be the same as for a an engine, an electric engine for a hydroelectric plant. That takes up lots of space, lots of weight, it's got lots of value. So if you look at the percent of the value of the good, and C is the cost of the inventory item, so I times C gives you that holding cost. Annual inventory holding cost is average inventory, which is Q divided by 2. Q is our variable, how much do we order? And annual holding cost per unit, which is C sub H, so it's 1/2 Q C sub H. So depends only on, also we have the ordering cost. If D is the annual demand and Q are the units ordered at each time, then D divided by Q are the orders placed per year. So the annual ordering cost is the number of orders per year times the cost per order. So it's D divided by Q times C sub O for ordering costs. So the total annual ordering cost, or total annual cost, is 1/2 Q times the cost of holding plus D divided by Q times the cost of ordering. And if you want to do D times P, which is the annual demand times the price that you're paying to get that. But that factor is fixed. It's not going to change. It's not going to affect anything. So we're only looking at the costs that we can control by this variable Q, which is what amounts we order in or what lot sizes we produce things in. So presto change, or you do a little calculus, you do a little solving of equations, and to minimize the annual cost is Q star, this is the answer, is 2 times D C sub 0 times the holding cost divided by, or the ordering cost divided by the holding cost, the whole thing taken a square root, not just the numerator. Because this slide has such a horrible summary, we're going to look at it differently in a minute. Calculating the reorder point. Well, if there is a reorder point, so this is a little extra, I don't think I'm going to give a problem on this. Depends on the lead time and demand rate. So what's the lead time? The lead time is L, and it's usually in days, not years. R is the rate at which, the daily rate of sales. So you look at how many days you sell divided by the capital D, and you get little d times L. So it's the demand rate times the lead time is your reorder point. So if we go back to this picture, and let's say it takes us 4 days to get an order in, I've got to go back 4 days of even sales and go up to here and say, ooh, when I hit this point, That's when I want to reorder so that when I run out, the new stuff's here. Now, how do you complicate these models even more? Is you end up adding, if D has a statistical distribution and L, the lead time and the daily demand rate, both have different statistical distributions. Let's assume normal with means and standard deviations. Your calculations get a lot more complicated pretty quickly. If I add in a perishability factor, like it's a grocery store where I'm buying tomatoes, and tomatoes don't last forever. They don't last like Papermate or Big Pens do, or iPhones or things of that nature. That complicates the model even more. But it all starts with the original 1913 economic order quantity that Ford Harris developed. So here's from Investopedia. Economic order quantity is the ideal order quantity a company should purchase to minimize inventory costs, such as holding costs and storage costs and order costs. This production scheduling model was developed in 1913 by Ford Harris and has been refined over time many times. The formula assumes that demand, ordering, and holding costs remain constant. So in other words, the demand doesn't change in a year, the ordering cost doesn't, the cost to order doesn't change over the year, and the holding costs remain constant for that whole year. The EOQ, or Q star, is the company's optimal order quantity that minimizes its total cost related to ordering, receiving, and holding inventory. The formula is applied in situations where demand, ordering, and holding costs remain constant over time, as we've discussed. So here we go. They're not using the same letters we're using, but that's okay. Q equals EOQ units. D is demand, that's the same. S is the order cost, which is C sub O in the other one. And holding cost is H, which is C sub H in ours. Per purchase order, per unit, per year. And you solve this and you get your economic order quantity. Good for us. Now, if you're looking at manufacturing, it looks like this. Economic order quantity. And there's a video in the Investopedia article which you can go look at. And I'll put a reference to the article and then you can watch the video. It's only 1:37, not as grueling as having to watch my 1 hour jobs. It's 2 times S times D divided by P times I. Well, let's look at what the 2 is absolutely the same, right? And instead of demand, I have S. S is setup costs. So it's not D, that's D is D. Demand rate, but let's call it annual demand here. The setup cost is in lieu of order costs, the S part here, or C sub O. On the bottom, we have production cost times the interest rate. What does it cost you times the interest rate of, that money? That's one way of looking at it. Another way from an accounting management, which is exactly the formula that you should probably focus on here for the few problems that we're going to have, is economic order quantity, or Q star, equals 2 times D times the ordering cost divided by the holding cost, the square root of the whole thing. So here's a problem. The material DX is used uniformly through the year. The data about annual requirement, ordering costs, holding costs of this material is given below. We have an annual requirement of 2,400 units. The ordering cost is $10 per order. It costs us 30 cents to hold a unit inventory for an entire year. Well, how do we solve the problem? And notice, in these kind of problems, everything comes out nicely. In real life, everything doesn't come out nicely. So the annual requirement is D. D is 2,400. So I want to put 2,400 for D. The ordering cost, C sub 0 is 10. I put 10 in for C sub 0. And the holding cost is 0.3 cents. So I have 2 times 2,400 times 10. So that's 4,800 times 10, 48,000 divided by 0.3 is 160. Voila, it comes out so nice. Square root of 160,000 comes out to be 400. That should be how much I should order, or how much I should make at each time I make it or each time I order it. Isn't that wonderful? Well, we don't stop there. I want to look at the following. If I want to look at the number of orders per year, it's the annual demand divided by the EOQ. Well, my EOQ is 400. My annual demand is 2,400. So 24 divided by 4 is 6 orders per year. I'm going to make this thing 6 times per year. I'm going to order it 6 times per year. What's the order cost? Number of orders per year times the cost per order. 6 orders times 10, $60. What's the holding cost? Average inventory is, well, every time I order it, I'm going to get 400. So 400 divided by 2 is my average inventory. And I get 200 times 0.3 or $60. If your ordering cost and your holding cost aren't the same, you probably haven't done it right. Because this is optimal where ordering costs and holding costs are the same. It's not surprising if you know a little bit about calculus. Combined ordering and holding costs at economic order quantity is $120. You add the two costs together, and that's what you get. So, let's look at the next thing. We want to look at single period inventory. Well, this applies to inventory situations in which one order is placed for a good in anticipation of future selling, of a future selling season where demand is uncertain. This is like a clothing store ordering sweaters in a particular size and a particular color. We think we're gonna sell this much of these sweaters in this size in the next winter season. You place your order probably in February, March, or April. So they're producing it over the summer and shipping it to you. So it arrives in your hands. You've got them in your hands to put in your store in early September. So you're ordering way ahead of time. You have no idea really what the sales are going to be. And people are so horrible at forecasting this that, as we've talked before, come Christmas time, you can go into the store and get the sweater that used to be $100 probably for $30 or maybe even less, because they have to get rid of the inventory of this year's winter styles to make room for next year's spring and summer. So it's this kind of single period inventory. They may order the same sweater next year. They may redo the design, but it's always based on a single period. Now, this is originally called the news vendor problem. A news vendor buys newspapers from a publisher each morning for purchase costs of C dollars and sells them throughout the day at a revenue of R dollars. When he buys the papers in the morning, he doesn't know how many people will want to buy them during the day. He's standing at his little newsstand on the corner of 33rd and Thoid in New York, but he kind of knows the probability distribution, and that is, he knows the probability of each demand value occurring. If he runs out of papers, he can't buy more. If there are leftover papers at the end of the day, he can sell them back to the publisher for a scrap value or salvage value of V dollars, with V being much less than C. Otherwise, the news vendor can buy inventory risk-free. So, if we look at the single period inventory model, it's a marginal economic analysis. If you've taken, gee whiz, microeconomics strikes again. Compares the cost or loss of ordering one additional item with the cost or loss of not ordering one additional item. So CS, there's two ways of looking at it. We're going to look at two different formulas that are exactly the same. One uses cost, and one uses marginal. Uses the marginal language. So cost per item of overestimating demand. It's the cost of the item minus. So if you ordered, and it cost me $100. Let's say it cost me for those sweaters. It cost me $60 to buy those sweaters. And if I sell them, I'm going to sell them at 30, so I'm going to take a loss. My marginal loss for anything I'm left holding the bag with at the end of the selling season is $30. This represents the loss of ordering one additional item and finding it cannot be sold. Remember, marginal analysis for micro is that what happens if I do one more? On the other hand, the cost of underestimating demand is the sales price minus the cost of an item. So if I don't order the extra thing that I could have sold, in other words, if I sell out, I've lost out on the marginal profit, which is the sales price minus the cost of the item. So my sweater sells for 100 and it cost me 50 to buy it, I've lost out on $50 marginal profit. So now it represents and here, let me fix this up because this is not right. You're going to get the wrong impression. Oops. And if I was good at this, I would have no trouble. Okay. So this represents the opportunity loss of not ordering one additional item. That's your marginal profit. The optimal order quantity must satisfy this. The demand has to be less than Q star, where Q star is this number. And it's not really equal to this. Well, it has to equal Q star where the probability is this value. CU divided by CU plus S, but let's think of it this way. I think it's better. Marginal profit, which is, in other words, it's the sales price minus the cost of the item, divided by the sum of marginal profit plus marginal loss. Because really, I want to find, I'm looking at that probability. Marginal profit divided by marginal loss gives me a probability, and I want to find out where my cumulative probability is less than or equal to in such a sense that I can pick that as my demand. So let's look at a problem. This lady, Teresa Granger, is a manager of Chicago Cheese, which produces cheese spreads and other cheese-related products. Easy Spread Cheese is a product that has been popular, the probability, so we're only looking at one SKU, and she can make 10 cases, 11, 12, 13, 14, and let's assume it's a weekly kind of thing, and the probability, and maybe it's a seasonal cheese spread, they only sell it during Christmas or something. And from previous years, they know that the probability of selling 10 cases is 0.2, the probability of selling 11 is 0.3, 12.2, 13.2, and 14.1. So this is a uniform, this is a discrete distribution. It's not really a uniform distribution. It's a discrete distribution. It's just a probability distribution like rolling dice or picking cards or drawing cards from a deck that's well shuffled. In this case, we have 5 different states of demand, and we have probabilities of those occurring. There's 2 versions of this that normally are covered in a class perhaps like this, a discrete distribution like this, or using the normal distribution, which we're not going to cover, because then I'd have to refresh you on normal distribution and how all those tables work. So let's just do this. A case of Easy Spread sells for $100 and has a cost of $75. So the marginal profit is obviously $25. Any cheese that is not sold by the end of the week is sold to a local food processor for $50. And so Teresa never sells cheese that is more than a week old. Use marginal analysis to determine how many cases of easy cheese spread or spread cheese to produce each week to minimize the average profit. Now, I went and changed it a little bit and prepared a video that you can look at. But it gives you, and it goes through this analysis of how to solve it. And here's a YouTube that you can watch that's shorter than this one that will help you solve this kind of problems. So I'm going to give you homework this week that has some Little's Law. It has some economic order quantity problems, and it has probably one of these news vendor kind of problems. And again, it says uniform distribution, but that's not what it is. It's really a discrete distribution. Okay, so if this was in class, I would say, well, anytime I would say thank you, but if it was in class, I would ask for questions. Thank you very much for paying attention, and we'll talk again soon.